things that are not published or are going to be published. So I'll be speaking a little bit on closing the loop on QP. Many of you are using QP.
A little louder, please.
Sorry. I have my headache, so I will try to do my best. Like I will be speaking a few on closing the loop on task space. So the idea is that I give you what we're doing with the hints, okay, and I hope that we can interact more deeply after in some topics that you are interested in more deeply to know. So in our team we have like this MCRTC, which is open, because that we are controlling basically everything you will see in the videos totally. It is maintained by Kheddar, what you see here, and we are using it to control basically all our humanoids. And when we develop new knowledge, we try to implement it and force the students to really do this effort, which is intellectual sometimes, but so that others will benefit from it. It has been a tutorial on it for last humanoid, and maybe we'll renew this for the upcoming ones. And yeah, you can download it from this website. So, quick thing is that most of you are using the QP knows that the devil sometimes is when the things are really near like the bounds. Sorry for that. I don't know how to stop this. Yeah, I don't know why it's doing this. But anyway, so we have in this paper, which is coming soon, okay, two examples showing exactly for 1 degree of freedom, one task, why you cannot put any gains in the task space, in the task for the, we take a simple task, which is just a joint, a set point to go to desired position, okay, with a 1 degree of freedom robot. And you will see, in fact, that you cannot put any gain, it can go unstable. All these things, by the way, they come up because we didn't understand why the experiment we were doing, okay, were going wrong sometimes. And in fact, most of the things you see comes from the bugs and things that we talk about deeply after the experiments. Okay, and this is also one of the things that we noticed that when the robot, when you control your humanoid near the bounds for the balance and for the collision detection, for everything, when the constraints start to interact, then things blow up really easily. The solution we came up does not solve the interaction problem, but at least it solved the when you put gains on the task, you shouldn't worry anymore about how high are these gains, specifically for the robot that you are controlling the kinematics. And the idea is very, very simple. It's just adding integral gains, okay, in the constraints and in the tasks on the top of the ECDFs, okay, and we call it robust ECDF. So the experiment will show all of it. So this is, I'll go quickly here, because I have already said all this. And you will see here for the Honda, this is a very simple like set point task used in the QP in closed loop, of course. It means that you have the state of the robot coming back to your models of the QP, and you will see that stiffness of the task at 500 start to make the robot already oscillated. And where you will see in this right video that we can go higher and higher and up to the maximum we can put, okay, where the robot is still doing the task without moving much, okay, and not going into the stability. So he's raising the gains up to 800, and then it doesn't make sense a lot because it's to have maximum speed that we're going but for humanoids, you can see things more later here. Okay, well, we took a small task which is representative. It's not, of course, that we use, but we want to put the comb in the region which is under the feet, okay, which is a small square, and then we try to make the QP reproduce this in closed loop. Okay, and you will see that here the robot will simply fade. Then, okay, then Mohammed is grasping it. The same thing was with the ECDFs. Okay, so you will see even that in closed loop, the ECDF couldn't manage, of course, to correct this. Done. And then with what we propose, you will see it in a few slides. So in the paper there is like one toy example that highlights all these things that I'm speaking. And here we are using it without crank, without the separate crank, so that we have quite confident what we are doing. Okay, so I will stop here, okay, because the robot will do all this motion without failing. Okay, so and I will go to the next slide. We have been also working on impact-aware QP. We wanted to have tasks where we it's just me who wants to keep the QP as a magic box to solve many things. Okay, and one of the things we wanted to do is whether we can increase the QP to handle impacts, because when you do impacts and you do it in closed loop, then obviously the discontinuity in the velocity makes it that the system, the QP fails, okay, because there is no solution basically. The search space is empty instantly. Okay, and the idea is simply to consider that we rewrite some of the constraints by considering that the impact might occur in the net while we are nearby the impact. Okay, these impacts are intended impact, and we want to go to some impact pose. And in fact, what we do, we will rewrite the impact so that we pop up the post-impact velocity and we bound post-impact velocity. Okay, and then we can keep in a single QP, second order dynamics, live with first order dynamics and impact. Okay, and this is why we can do things like on the fly without necessarily stopping, and keeping the same framework and the same complex for the past. That was important for us to try to keep this kind of things. So other things that come up, I will not speak a lot about, but it's I wanted to say that we are driven a lot with industrial needs. Okay, that see potential in using humanoids, and but of course we have to showcase that the robots are potentially interesting. So in this work, it's what that appeared today, okay, online in case. So we are trying to combine SLAM and also like visual tracking, because the problem was that we want to manipulate objects when we automate, when we do the working, and in fact the perception is important to know. So this benchmark is given by an industry. We have to roll these bobines of 120 kilo, okay, by humanoid, and then put them inside, and then we have to unroll them, take the bobine, which is take the intercalary, which is in fact deformable things, and we have to pass it somewhere. We had also the experience with Airbus, and what I wanted to say is that most of the time the problem is that the arms are not well designed. Okay, and my suggestion is that if you want to design a humanoid robot, we will better remember that the most important thing is the arms and the head, because it's what the people will do once you walk. Okay, you want to do something with your arms. So the legs is important, but that's also the reason why in recent work we started to design new humanoid with BIT. But my first thing is that please first let's design the arms, because this is the most important thing. And this reasons a lot what Florian was saying. So we have integrated, in fact, the control basically the design. You can see here that we wanted the arm, in fact, because the example we have is always to work in cumbersome environment. And we noticed that if you don't have an arm that is, when you move it, reaches the same space, so you might, same unit space, you might run into a lot of problems. And here is for driving that we conceive this arm, and we are still closing the loop. So you are not doing it just for the control. And it was important that that the test first the arm.
Is it a feature or a bug?
So here the robot is fixed up, of course. It is, then we are starting now to think about the torso, and by the end we will probably do the legs. Okay, so I go next to the other slide. Okay, that was in the design to try to get also the human arm to get in the same picture. Okay, I think, how much time do I have?
3 minutes.
3 minutes. This is simply a last word that we wanted to make the robot. We had also two artists that wanted to do a show with you on the robot, and they wanted to have synchronization in the motion. Okay, and this paper has recently also appeared. It was challenging to synchronize, okay, the robot with the person. Okay, because you have to guess the exact timing, because the position doesn't really matter here. You really need to land at the same timing, and when you do the motion with the whole body, okay, you have to do it also in the same timing. Because when you end the motion with your hand, the robot has to end it. It doesn't matter really that you follow exactly the same pathway and the same path length, okay, but what matters really is that you do it in synchrony. So for here, the solution was for the arms. You have like invariants that tell us basically which is the minimum jerk, okay, that might have, okay, that you have used, and then added a little bit of deep learning on top of it. But for the next, it's mainly deep learning. So we do steps with the human, and we saw whether we can guess, okay, at the first iterations, okay, when you lift your the leg, where you would probably end. Okay, good. So, and then I go to this last, because this is an unpublished work that I call adios stabilizers. So I think that people who do human understand what I am talking about, these stabilizers. But this reason more about probably the last talk. We were saying, sorry, it's not. Yeah, well. Simply saying this is known stuff. Okay, we have an inverted linear model. Okay, this change of variable, when the comp converges to DCM, you know DCM will derive from the ZMP. And of course, the question was, is there a trajectory such that the ZMP, so that the DCM is bounded? And Lanari's group, we have come up with this intrinsic stability formula that we are using. Okay, we are using on the top of this to build what we want. What we want is that I was really angry that when you do the control guys, you have to say this stabilizer. Okay, and I didn't know why we cannot do the control directly from the MPC and close the loop on the MPC. And so basically, if you want to close the loop on the MPC, so the DCM can be captured on the ZMP. If you take this equality, if you take the previous equation of the intrinsic stability, you can just put the ZMP on the ZMP and it's captured. Okay, but this is not realizable, of course, because the ZMP has a delay. And when you try to integrate the ZMP model inside, the ZMP inside the model with the lags, because the ZMP has always the lag, then you cannot capture any longer the ZMP. Okay, and basically what you do, this is also knowledge, okay, classical knowledge, is then you take, you correct the ZMP reference using the DCM to back to BC. Here I took the example of the PID, okay, and I don't know why it's doing like this. Stop. Yeah, with this example you can of course capture this, but it has some things that I do like. The fact that the high-level planning is disconnected now from the state of the real robot, and that this leads also to branches in the planning and the constraints. Okay, and what we propose is simply to close the loop on the pattern generator by integrating the ZMP model explicitly in the pattern generator. It means in the MVC. So we reformulated the problems like this. And there are, of course, so while we have integrated now, okay, the ZMP, the first order model ZMP with a delay, okay, that we consider. Then we added a few things, classical and usual, okay, the constraints. And the most important is that for this, I wanted really to test it in all the platforms that we have. And on flat grounds with banks and compliant floors and outdoors. Okay, and these are the only parameters that you need to tune. Okay, the ZMP first order model, the FDM first order model, and the FFDC is the force distribution of the two legs. Okay, gain and also the COP gain. And this is the only thing that you need to tune, and then this is the video, and it's the end of the talk. Sorry for getting like really.
We have 3 minutes for questions.
Yeah, I thought you presented some results on the impact area control. So in that system, you only change the controller without modifying or change some device, I mean the hardware. Do you need some, the impact area sensor?
Yeah, thanks. It's a very good question. So for me,
Yeah.
you cannot control impact. For me, you can control the pre-impact. You can control the post-impact. But the impact is the issue of the hardware. Okay, if you have a hardware that is resilient to what you want to do as an impact, I mean, there is no control that will do magics. Okay, at the end, when you do the impact, okay, it's your hardware that has to be resilient to that. Okay, so what we do is mostly pre-impact, post-impact, but it doesn't control really the impact. And this is yes, the Japanese working outdoor. So it's a miracle that it's working. You see that there is a spot between the two arms and the torso, which just because the two actuators of the shoulder are not working. Okay. And we have 3 months of shortage to get that. And here there is no stabilizer, so we are working on closed loop on the PC. Yes?
So that new humanoid you showed, do you see that as like taking the place of HRP5 and HRP2, or is it just like another option? The one.
Yeah, the one that you saw is we co-developed with Kawasaki Heavy Industry. I think it's not a secret now.
Yeah.
And it is supposed to be replacing the robots that we had because it is designed now really for manufacturing. So we contributed by sharing all the knowledge that we had gathered from Airbus and the other industrial partner. And I think this robot is really very robust. It can jump from high stairs on one leg, and I think we can do much more things with it.
Thank you.
Thanks so much, Ahmed.